the book presented a series of equations that they worked out in section 2.5, and I wanted to go through how to do that. So there's actually two methods that I'll show you how to derive these motion equations for uniform acceleration. One method is using a geometric-based method on the position, velocity, and time graphs that we've used before. The other method is to follow the book's method. And there's other ways to do it as well. This is what we're doing. So just to start out with, we have our basic equations that we start with speed equals distance over time. This is for average speed. And on our list of motion equations, I actually labeled this as motion equation number 2. Our average velocity equation is similar. We have instead of distance, which is measured on the odometer, we have displacement, and this is a vector quantity. And that's actually equation number 3. Next, we have average acceleration, which is delta v over delta time. So our change in velocity over change in time. And that's actually motion equation number 4. And all of these motion equations can be used whether or not we have constant acceleration. So these are independent of the type of acceleration. In math class, we typically would replace an x1 with just a plain old x, some future value of x. And in physics, what we tend to do is for time 0, we typically use time 0 equals 0. So we zero that out. And this time is some time in the future. And this x is just some other value of x on the graph we'd like to find. All right, so that's the type of simplification we're going to do. So it simplifies our equations to something that looks like this. All right, so this is just some future x value at some future time. This is some future velocity at some future time. So from our last page, remember, this is just delta v, and this is delta t simplified a bit. All right. Now, if acceleration is uniform or constant, how can we compare the average acceleration to the instantaneous acceleration? This is a simple answer, as it turns out. Your acceleration at any instant is the same as your average because it's constant, and so they are equal. We're going to start out by taking this equation up above, and I asked you just to solve for velocity. Let's see what we come out with. So it turns out instead of average acceleration, we can just call it a. So because our average acceleration equals our constant acceleration. All right, so I have a equals v minus vx naught over t. And I just want to solve this equation, this simple equation, for velocity. And to do that, we just multiply both sides by time to get rid of our time. All right, and then we can add vx naught to get our v isolated. And when I do that, when I add vx naught on both sides, I get a times t plus vx naught equals v. All right, and you'll notice that's equation number 6 on our list of equations. This, by the way, the fact that our acceleration at any time is constant, is equation number 7. When we had a velocity versus time curve for a constant acceleration situation, it turns out it's a straight line. All right. And if it's a straight line, then we can take our initial velocity and some final velocity. If we wanted to find the average is going to be in the middle. And to get that middle point, well, since it's a straight line, we just use the midpoint formula. All right. So to get the average velocity, v average, or v bar, all we do is we take the average of these two values, the starting value plus the ending value, divided by 2. And that equals our average value. So our average value, when we have constant acceleration, this is not true if we don't have constant acceleration. So this formula up above is just for any situation. This is just our good old friend delta x over delta t, simplified a little bit. So this is good for all motion, whereas this equation is only good for uniform acceleration problems. Well, if I have two equations that relate the same quantity together, I can set them equal and see what happens. So we're going to set one equal to the other, and we'll see what we get out of this. All right. And I asked you up here to solve for delta x, and this quantity right here is my delta x. All right. So to get delta x by itself, all I'm going to do is multiply both sides by t. So what I end up with is delta x equals v1 plus v0 over 2 times our t, which is the same thing as, remember, t just represents delta t, as we start at 0 typically. All right. And you'll notice on our list of equations, I think this is equation number 9 that we just worked out. All right. I'll let you try out the next couple of pages on your own and see what you come up with, and we'll go through that together in class.